In this video, we are going to take a look at what happens when something dissolves and the extent to which it dissolves and how that relates to equilibrium. So what we're used to seeing is on our solubility table, we looked at substances and saw that they were either soluble or insoluble. So let's see what that really means. We're going to take table salt and say we throw a little chunk of table salt of sodium chloride in a beaker containing a little bit of water. So that sodium chloride starts out as a solid and then it dissolves because sodium chloride is soluble and it turns into aqueous sodium ions and chloride ions. So that little clump of stuff that we threw in that beaker breaks up into teeny tiny little pieces, those little ions, and eventually the little clump goes away because sodium chloride is soluble. It goes away and turns into lots and lots of little tiny sodium ions and chloride ions. So that's what happens to sodium chloride because it's soluble. What about what happens to silver chloride? Well, according to our solubility table, silver chloride is not soluble in water. So if we threw a chunk of silver chloride in that water, it would just sink to the bottom and none of it would turn into ions. Now that doesn't necessarily happen. And this is where equilibrium comes in. If in reality, if we take a chunk of silver chloride and we throw it in water, it will not just sink to the bottom and not produce any ions. What will really happen is it will produce a few ions depending on how much it can dissolve. There are varying degrees of solubility, and silver chloride happens to have a very, very low solubility, but not zero. So if we break it apart and we represent this as AgCl in equilibrium with water, in equilibrium with a dissolving process, what we end up with is silver ions and chloride ions in equilibrium, in aqueous equilibrium, and just a few particles. Now, it's so few particles that all solubility tables probably have silver chloride listed as insoluble, but we can now show varying degrees of solubility using a solubility product constant. And it's just the same as our equilibrium constants, but it's dealing with the solubility of a substance. So we have silver chloride in equilibrium with the ions, the silver ion and the chloride ion. And we represent KSP exactly how we represent equilibrium constant. And we can have a KSP constant expression just like we would have an equilibrium constant expression. So we would represent our products, the concentrations of our products, over our reactants. However, we have a problem in this situation. Our reactant is a solid, and we don't represent solids in equilibrium constant expressions. So we will represent it as a 1 in our reactant side. So really what we're doing is we're just representing the dissolved ions when we have an equilibrium constant expression that relates to solubility. So for the silver chloride, the KSP, or the equilibrium constant for the solubility of this, is very, very low, 1.77 times 10 to the negative 10th. What this tells me is that AgCl does not dissolve very much. It will dissolve somewhat, to some extent, but not very much. So we're going to be using KSP, or the solubility product constant, to represent varying degrees of solubility instead of just soluble or not soluble. Another definition here, molar solubility. The molar solubility is the quantity that dissolves in a certain amount of liquid, usually in moles per liter, to make a saturated solution. If we know the KSP, we can calculate the molar solubility. So remember that KSP for silver chloride is very, very low, 1.77 times 10 to the negative 10th. If we're setting up a reaction for this, we would just be producing ions. The solid isn't going to be represented, so we leave it out of our icebox. Now I'm going to set up this icebox with 0 as my initial concentration of my ions. The change in concentration will be plus X for each because of the stoichiometry, the balanced equation, and the equilibrium concentration will be represented by an X for each. So the KSP is really equal to X squared in this situation. To solve for X, we take the square root of the KSP. So 1.77 times 10 to the negative 10th. So if I type all of this into a calculator, I can solve for x. I can solve for that molar solubility. So the square root of 1.77 times 10 to the negative 10th is equal to 1.33 times 10 to the negative 5th. This is my x value. This is my molar solubility of the silver chloride. This is how much I can dissolve. I can dissolve 1.33 times 10 to the negative 5th moles of silver chloride per liter in this water at this temperature. So x is equal to 1.33 times 10 to the negative 5th moles per liter. Let's try another problem here. We have lead 2 chloride. Calculate the molar solubility of lead 2 chloride in pure water. The KSP of lead 2 chloride is 1.17 times 10 to the negative 5th. So I'm going to set up this dissolving equilibrium equation. We have the solid lead chloride on the left and the ions in aqueous solution on the right. Notice how we have 2 chloride ions. That stoichiometry is going to come into play in a little bit. So the PbCl2 breaks apart into 1 Pb ion and 2 Cl- ions. Our KSP is equal to the product of these 2 ions. So multiply them together. We have Pb2 plus and the concentration of Cl minus squared because of that coefficient there. That is equal to 1.17 times 10 to the negative 5th. I'm going to set up my ice box. I have 0 of each to begin with. The change is plus x for the Pb and plus 2x for the Cl minus because of the coefficient there. So the equilibrium concentration of the Pb is going to be equal to x. The equilibrium concentration of the Cl minus is going to be equal to 2x. So I'll set this equation up. 1.17 times 10 to the negative 5th is equal to x times, and then in parentheses, 2x squared. And that's going to be equal to 4x cubed. So all I did is I just plugged in those x values into my KSP equation. I'm going to divide both sides by 4 so that x cubed is by itself. And then I'm going to bring up my calculator here and I'm going to take 1.17 times 10 to the negative 5th. And I'm going to divide that by 4 so I get what my x cubed. My x cubed is 2.925 times 10 to the negative 6th. So what I want to do is to find x, I want to take the cube root of this. And some calculators really don't let you do this very easily. They don't let you take strange roots of numbers very easily. So I'm going to show you kind of a shortcut or a trick. So to take the cube root of this, I would just take this number raised to the power of 1/3. So that's how you can get around taking these strange roots of numbers if you don't have those buttons on your calculator. So I'm going to take 2.925 times 10 to the negative 6th, and I'm going to raise that to the 1/3 power. That's going to give me 1.43 times 10 to the negative 2nd. And that's my molar solubility. That's how much PbCl2 will dissolve in pure water, 1.43 times 10 to the negative 2nd moles per liter. Now notice that's not my equilibrium concentrations necessarily. If I wanted my equilibrium concentrations, I would take those x's and sub them in for the Pb and the Cl concentrations, but all I'm looking for is the molar solubility. So how much of that PbCl2 will dissolve? Now, in this situation, we're going to be given the molar solubility and having to calculate the KSP. So what I want to do is I want to write my equation for the dissolving of this silver sulfate. So we have silver sulfate dissolving, and that starts out as a solid, and it dissolves into 2 silver ions in aqueous solution and a sulfate ion. So SO4 with the -2 charge in aqueous solution. I'm going to set up my ice box here. So I'm starting with 0 of each and my solid, of course. And then the change is going to be plus 2x for the silver and plus x for the sulfate based on the coefficients. So my equilibrium concentration for the silver will be 2x and for the sulfate will be x. So my KSP, we're calculating this, and this is going to be equal to the concentration of the silver ion squared times the concentration of the sulfate ion. So I'm setting up this sort of equilibrium constant expression with the KSP and substituting in my x values. So I have the KSP is equal to the product of 2x squared times x, which is really equal to 4x cubed. Now my x is equal to 1.4 times 10 to the negative second. That's my molar solubility. That's how much Ag2SO4 will dissolve. So I take that x and I plug it in to the 4x cubed, and I just solve that. I just type all the rest into my calculator and figure out what the answer is, what that KSP value is. So I'm going to do this so that the order of operations is correct. I have 1.4 times 10 to the negative second, and I'm going to cube that, and then I'm going to multiply it by 4, so I get 1.0976 times 10 to the negative fifth. And so my KSP is equal to 1.1, that's 2 significant digits there, times 10 to the negative fifth. There are no units on this, it's just a KSP value. It's the solubility product constant for the silver sulfate in pure water at a specific temperature. Let's finish up this video by talking a little bit about saturation. So if we have a 5.6 times 10 to the negative 1 molar solution of Ag2SO4, do we have an unsaturated, a saturated, or a supersaturated solution? Now, in order to answer this question, we need to know the molar solubility of the silver sulfate, which we found on the previous example was 1.4 times 10 to the negative second moles per liter. That's how much can dissolve. That's the total amount, the maximum amount that can dissolve to create a saturated solution. So now what we're going to do is we're going to compare the value that we were given in this question with the molar solubility. And if this number is less than the molar solubility, then that means that we could dissolve more in it. That means that we have less dissolved than what we fully could dissolve. We have an unsaturated solution. And on the reverse side of this, if we have if we're given a value that is more than the molar solubility, what we have is a supersaturated solution, and in specific conditions under specific temperatures and pressures, we can actually have a supersaturated solution, meaning more solute is dissolved than what the solution should be able to hold. That's a supersaturated solution. So where does this value fall? Is it less than the 1.4 times 10 to the negative 2 moles per liter? If it is, then we have an unsaturated solution. If this number is greater than 1.4 times 10 to the negative second moles per liter, then it's a supersaturated solution. So what we have is 5.6 times 10 to the negative 1 moles per liter, which means we have a supersaturated solution.